Find the minimum shipping cost. In this problem, cases of materials need to be shipped from 3 factories to 5 warehouses. Warehouses are located in Los Angeles, Dallas, Chicago, New York, and Atlanta. The factories are located in Detroit, Washington, D.C., and Nashville. In a given month, the factory in Detroit can produce at most 1.2 million cases of materials. The factory in Washington, D.C. can produce at most 700,000 cases of materials, and the factory in Nashville can produce at most 1.5 million cases of materials. If we assign variables S for supply, S equals 1, S equals 2, and S equals 3 refer to the maximum monthly supply from the factories in Detroit, Washington, D.C., and Nashville, respectively. This data can be summarized in a table. The warehouses in each of the 5 cities have monthly demands, which are 1.1 million cases of materials needed in the Chicago warehouse, 400,000 cases in the Los Angeles and Dallas warehouses, 500,000 cases in the Atlanta warehouse, and 800,000 cases in the New York warehouse. Assigning the variable D for demand, a second table showing the demands for these 5 cities is created. Since there are 3 factories and 5 warehouses, there are a total of 15 possible routes cases of materials can be transported from a factory to a warehouse. Therefore, there are a total of 15 decision variables, x sub sd, used to identify the quantity of cases transported from factory S to warehouse D each month. There are also fixed costs, C sub SD, used to identify the cost of transporting 1 case of material from factory S to warehouse D. The X vector will contain the 15 decision variables, and the cost vector will contain the 15 transport costs. The objective function will be to minimize the product of C transpose X. The transport costs are known and shown here in units dollars per case. As for the constraints, each factory cannot produce more than its capacity, and each warehouse must receive its demanded quantity. Lastly, all 15 decision variables should be non-negative. For the 3 supply constraints, we'll introduce slack variables S1, S2, and S3, so the constraints are in standard form. Initially, the X vector will equal 0, and the slack variables will equal the right-hand side. Since the 5 demand constraints are equality constraints, artificial variables v1 through v5 are added, where artificial variables are also initially equal to the right-hand side for each constraint. Setting up the network tableau, we begin with the slack variables and artificial variables in the basis, and the 15 values in the X vector as non-basic. The entire tableau has a total of 25 columns, 23 variables, the right-hand side B, and the first column which lists the basic variables. To put the tableau into canonical form, we must perform a pivot operation about the non-zero values of the artificial variable columns. Rows V1, V2, V3, V4, and V5 are subtracted from row Z1, and the tableau is now in canonical form. Now we are ready to begin the simplex algorithm. From pricing out, we'll select variable x14 to enter the basis in place of artificial variable v4, since 11 is less than 12. Pivoting about the value x14, shown in red, 1 times row x14 is added to row z1, 0.15 times row x14 is subtracted from row z2, and 1 times row x14 is subtracted from row s1. And the tableau is in canonical form. Next, the variable x21 is chosen to enter the basis in place of artificial variable v1, since 5 is smaller than 7. This time, pivoting involves adding 1 times row x21 to row z1, subtracting 0.35 times row x21 from row z2, and subtracting 1 times row x21 from row s2. After just 2 iterations of the simplex algorithm, our phase 1 objective function value has decreased from 32 to 16. However, there are still 3 artificial variables to be removed from the basis before we're done with phase 1. Next, we'll choose variable x35 to enter the basis in place of artificial variable v5, since 8 is a smaller positive number than 15. Pivoting about x35, row x35 is added to row z1, 0.85 times row x35 is subtracted from row z2, and 1 times row x35 is subtracted from row s3. Next, we'll choose variable x12 to enter the basis in place of slacked variable s1, since 1 is less than 4. Pivoting about variable x12, we'll add 1 times row x12 to row z1, subtract 1.05 times row x12 from row z2, and subtract 1 times row x12 from row v2. In the next iteration of the algorithm, we'll select variable x33 to enter the basis. Variable x33 will replace artificial variable v3, since 4 is less than 7 from the ratio test. Pivoting about variable x33, 1 times row x33 is added to row z1, 1.6 times row x33 is subtracted from row z2, and 1 times row x33 is subtracted from row s3. From pricing out, variable x22 is selected to enter the basis, and will take the place of slack variable s2, since 2 is less than 3 from the ratio test. Pivoting about x22, we'll add 1 times row x22 to row z1, subtract 1.8 times x22 from row z2, and subtract 1 times row x22 from row v2. From pricing out, the next variable we'll choose to enter the basis will be variable x34. It will take the place of artificial variable v2, since 1 is a smaller positive quotient than 3. Pivoting about x34, we'll add 1 times row x34 to rows z1 and x12. Subtract 1.6 times row x34 from row z2, and subtract 1 times row x34 from rows s3 and x14. Since there are no more artificial variables in the basis, their sum equals 0, and we have achieved an initial feasible solution. Phase 1 is now complete. The rightmost column indicates the values of the basic variables, which are in units of 100,000 cases, to be transported from Factory S to Warehouse D each month. For example, X12 equals 2. This means 200,000 cases of materials are shipped from Factory 1, which is Detroit, to Warehouse 2, which is Los Angeles. Similarly, X22 equals 2. This means 200,000 cases are shipped from Factory 2, which is Washington, D.C., to Warehouse 2, which is again Los Angeles. The remaining transport routes are sketched in, and for clarity, the city names are removed. Since slack variable S3 equals 2, this means Factory 3, Nashville, can ship out 200,000 more cases of materials than it currently ships out according to this schedule. We can confirm this solution is feasible by looking over the supply and demand constraints. The sum of the cases from the Detroit, Washington, D.C., and Nashville factories is at most the capacity of the factory. Similarly, the sum of the cases delivered to Atlanta, Los Angeles, Dallas, Chicago, and New York equal the demanded quantities at each location. Furthermore, all variables satisfy the non-negativity constraints, and all non-basic variables equal 0. Based on the initial feasible solution, the total shipping cost can be calculated as C transpose X, which equals $2.285 million. Since phase 1 is complete, we can remove row Z1 and the columns for the artificial variables V1 through V5 from the tableau. Now we'll begin pricing out using the reduced cost coefficients from row Z2. As it turns out, non-basic variable X25 has the lowest reduced cost coefficient of negative 0.75. Variable X25 will enter the basis for variable X22, since 2 is the lowest positive ratio. The pivot operation involves adding 0.75 times row X25 to row Z2, adding 1 times row X25 to rows X12 and X34, and subtracting 1 times row X2 from rows X14 and X35. After pivoting, the only remaining negative reduced cost coefficient is the one for variable X13. Based on the ratio test, X13 will take the place of X33. And after pivoting, an optimal solution is found because there are no more remaining negative reduced. Returning to our map, the optimal shipping routes are shown, where the supply constraints are maintained, as well as the demand constraints. The total costs associated with this optimal shipping schedule equals $2.035 million. Looking back at the possible solutions, the answer is B.